Let's continue our discussion on the terminology and properties of binary tree. Specifically, we want to talk about what a proper binary tree is. Let's now look at the definition. A binary tree is proper if each internal node has two children, exactly two, no more and no less. And so this will be one example. Let's see why this example tree here will be a proper binary tree. And let's take a look. First of all, you can for now just disregard this part over here. We're going to talk about it in just a moment. Okay, let's take a look at this example tree. Number one, why would it be a binary tree? Because for every node over here, it has at most two child nodes. So that'll be the definition for a binary tree. You can see 1, 2, and for this node over here, 1 and 2, and etc. And why would this binary tree be also proper at the same time? In that case, the number of child nodes for every internal node, for example, for this internal node, you got exactly two child nodes. And for this internal node over here, you got exactly two child nodes. And you do the similar checking on all the internal nodes in the tree. But what about external nodes? In that case, by definition, they got zero child nodes, in which case we don't have to worry. We only worry about internal nodes. Right, so that's really the definition. You want to make sure you understand for every internal node, we have to check they got exactly two child nodes. And also before that, you also want to understand what does it really mean for the tree to be binary at the first place. For example, let's say this. If I just introduce another child node over here, that's the only change I made, would this still be a proper binary tree? The answer should be no, because it's not even binary in the first place, because in this particular internal nodes, it got more than two child nodes. In that case, it wouldn't be binary. Right. And then we're going to talk about some property for a proper binary tree, which is very interesting. Let's take a look. Let's say given the binary tree, which is, first of all, non-empty. It contains at least the root node, at least one node. And also, it is proper, meaning that for every internal nodes, we got exactly two child nodes, and we are not concerned about any external nodes. And also, let's say we got a certain number of internal nodes. Let's say it's n with subscript I standing for internal. And also we got certain number of external nodes. Let's say n with a subscript e. So we get ni and ne. Right? So this will be our convention for the discussion for this property. And so this will be the property we want to somehow argue about formally, meaning that we're going to do some proof. So we want to say that for any non-empty proper binary tree, right? Notice that these are the two assumptions we're making. We need them in order to prove. The number of external nodes will be equal to exactly the number of internal nodes plus 1. But now, how do we actually argue about the correctness of this? And I think doing this proof formally together with you will actually help you think about how you can really construct the binary tree, especially proper binary tree, recursively from scratch, and also to really understand how you can do proofs on trees. It's actually a very valuable exercise for us to do together. Let's now do it. And the way we're going to do it is by a very common, very powerful technique called mathematical induction, which I'm pretty sure you learned about from other math courses. Let's see how we can apply this in our context. A very typical way to do mathematical induction on the recursive structure of a tree is by using its size. Because the size of the tree can definitely start from the smallest one, which will be non-negative, like an empty tree. But in our case, we assume the tree is actually non-empty, so our smallest case should really start with a size 1. But it's a very typical base case as well. Let's write it down for the base case just to argue to get a feel about how we can proceed with the formal proof. For mathematical induction, you should always start with some base case, and then we'll go for inductive case as well. So base case. A proper binary tree with size 1. How do we visualize such a proper binary tree? Well, in that case, it will be just one node specifically, just one. And for this node over here, is it internal? It is not, because this node here has no children. In that case, it will still fit into the definition for binary proper binary tree, because there is simply no internal nodes, meaning that we cannot find any violation in this particular one node binary tree, in which case we got any internal nodes which got less than 2 child nodes. We don't have that violation. Right? It's really important to see why the base case will actually satisfy. there's no internal nodes. That implies the proper property is satisfied. And more precisely, because we just cannot find any violation, because there's simply no internal nodes, so of course that means you cannot find any violation. It's pretty much like the empty set mathematically can satisfy any property, because you just cannot find any violation member in the empty set. I can say every element in the empty set is positive. I can say that because you cannot prove to me by finding a witness in the empty set saying that that member is not positive. Similar idea. Without violation witness. Right? So that's for the base case. So what about the recursive or inductive case? Let's talk about inductive case. Inductive recursive case. In that case, we have to somehow assume the arbitrary number of nodes in the already proper binary tree, and then we try to see how we can grow the size of the tree just by a little, and so that with such growth, the tree will still maintain to be proper. So what do I really mean? Let's now consider this example proper binary tree, and let's count about the numbers of internal versus external nodes. In the case of the internal nodes, let's now see. So we want to count ni over here. And let's mark all the internal nodes in the tree. This is internal, this is internal, 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 and also internal. 1, 2, 3, 4, 5. We got 5. So in this case, we got internal nodes will be equal to 5. What about external nodes? Everything else will be external nodes without any child nodes. You can see at the leaf level. 1, 2, 3, 4, 5, 6 magically is exactly the number of internal nodes plus 1. External nodes will be exactly 5 plus 1, which will be 6. Let's now talk about how we can create a new tree by growing the current binary proper tree just a little. Can I just grow the tree by just one node? For example, I can say, well, apparently you cannot grow the internal nodes, in which case it would not be binary anymore, would it? Can we just grow the external nodes by just one node over here? The answer is no, because if you do that, the resulting tree would not be proper anymore, because every internal nodes, including this new internal nodes over here, must contain exactly 2 child nodes. So if you only grow it by 1, it wouldn't work. So you must grow it by 2, and that'll be the smallest extension we can make to really grow the any arbitrary binary proper tree. Right? It's a very important insight to really remember why we cannot grow any internal nodes, and also why we cannot only grow one node for the external nodes. We must grow exactly 2 internal nodes. You want to review what I just mentioned, what I just explained earlier. Right? So let's now do that. If I do that, let's say if I try to grow this node over here, let's say I want to have 1 left node over here and 1 right node over here. So this will be the smallest extension I can make. In that case, we have to recount about the internal and external. And the way I'm going to do this will be, let's say ni internal nodes prime, meaning that after the growth, after the extension. And also I got ne prime, the number of external nodes after the extension. And let me now change the color. This node over here should not be external anymore. It has been converted into an internal nodes, which will be over here. And these two will be just external nodes. Right? You can see the numbers of the ne, the values for ne and ni have just been changed. But do they still have this particular relationship inequality that we talk about? Let's see. So what we got is how many external nodes do we have? 1, 2, 3, 4, 5, 6, 7. We got 7. And what about the number of internal nodes? In that case, we got 1, 2, 3, 4, 5, 6. Magically, the relationship still holds over here. Right? You can see 7 is exactly 6 plus 1. So this really tells us whenever you want to grow the size of the proper binary tree, starting from the base case, the only way you can make an extension is to choose some external nodes and then try to add 2 child nodes. In that case, it will guarantee to result in another larger proper binary tree. So that's really the idea about inductive over here. And let's now try to generalize this. Remember how we can draw a tree in general, including binary tree. We use a triangle. So let me do that. We have an arbitrary sized proper binary tree over here, but it should not be the base case anymore. So the size should be strictly larger than 1. Let me write it down. We assume that this tree over here is a proper binary tree. Proper binary tree with the size strictly larger than 1. So that's indeed the inductive case. And we assume that the number of internal nodes is actually ni. And the number of external nodes is actually ne. Right? But if you like, I can be more consistent with the color. So let's say the case of external, it would be ne. Internal would be ni. And we should really make a so-called inductive hypothesis to say, given this, we have already this relationship satisfied, so that when we actually try to grow the size of this proper binary tree that's arbitrary, we can still have this relationship maintained. That'll be the idea. Let's take a look. So what we want to do is, let me write it down over here. So we have the so-called inductive hypothesis. Inductive hypothesis, which will be the ni is exactly, ne actually. Ne is equal to ni plus 1. So this will be very important to actually note. Inductive hypothesis. We will need this later when we actually want to work out the equation when we get a new tree. And how can we grow the tree? As we learned from this particular example, the only way you can actually grow a proper binary tree is by choosing some external nodes and then try to convert it into internal by adding 2 child nodes. It gotta be exactly 2, right? Let's try to visualize this over here in the general tree. Let's say I try to find some external nodes, maybe around over here. I can choose any arbitrary external nodes. In that case, I'm going to add 2 external nodes over here. So it will be 1 over here, and then another 1 over here. So that'll be the idea. And let's now work out exactly how the numbers of the internal versus external nodes are going to change with this growth. Let's start with external nodes. So I can say ne prime. Remember, the prime means after the growth will be equal to, thinking this way. This node over here used to be external, but now it has been converted into internal. So that one is gone. So we should really say minus 1. But at the same time, we're adding 2 external nodes over here for the growth. So that should be plus 2. So let's now write this. It will be the original ne before the growth. First of all, minus 1. Because we have converted this used to be external node into internal. But at the same time, we're adding 2 external nodes. Minus 1 and plus 2. It's really important for you to understand why the minus 1 and why the plus 2 over here. It's really important. It's just explained. So this will be exactly ne plus 1. And what about the internal nodes? How is it going to change? Ni over here after the growth will be equal to, this used to be external, but we're converting that into some internal nodes over here. So that means the number of internal nodes will be incremented by 1, right? Number of internal nodes plus 1. Let's now take a look at these 2 numbers over here, ne prime and also ni prime, right? 1 is equal to this, and 1 is equal to this. Now we want to argue why this value over here is 1 plus this value over here. If we can prove it, that means we are done, right? Let's see how we can work out the equation. Right, so let me just write it down over here. Let me continue just from over here quickly. Okay, so the number of external nodes over here is exactly equal to the number of external nodes before the growth plus 1, which we know by the inductive hypothesis. Inductive hypothesis. We know that NE is exactly equal to NI plus 1. NI plus 1. And then plus 1. And we know that Ni prime, as we worked out earlier, should be equal to Ni plus 1. So this part over here, we can replace it by Ni prime. Let's now write it down. So this will be equal to, so this part here is simply Ni prime, and then the original plus 1. So that's exactly the proof we are aiming for. You can see now we got Ne prime is equal to Ni prime plus 1. So now we have proved it. So that'll be the end of the proof. Okay, so let me just put a circle over here just to indicate the end of the proof. It's a very simple proof over here. However, it does require some insights about how you can prove mathematical induction on binary tree or any general tree, which is on the size of the tree. All right, so you can now review the proof and make sure you understand the steps, and you can also see the written form in a slightly different way. Well, pretty much consistent, but maybe you can find some other details. I should really combine the proofs from both parts and try to see why the proof should be done in this way. I think the visualization I did on the iPad over here does give you a little bit more intuition about how you should really think about the arguments we are making using mathematical induction. All right, so let's now move on to talking about some application for binary tree.